Just like there are rules for derivatives of functions, there are rules for derivatives of vector-valued functions. So let u and v be vector-valued functions and f be a scalar-valued functions. So what that means is that f is a regular function that we like to think about, like f of t in this case equals t squared. So u, v, and f are differentiable at a point t, and c is a constant vector. That means that c is some numbers vector a, b, d, where a, b, and d are constants. So the first rule is that the derivative of a constant vector is the zero vector. Second, we have the sum or difference rule, that the derivative of vector u of t plus the derivative of vectors u of t plus v of t is the derivative of vector u plus the derivative of vector v. We have the product rule. So we have the derivative of vector u of t times the scalar valued function f of t, and that is the derivative of f of t times u of t plus f of t times the derivative of u of t. We have the chain rule. The derivative of u of f of t equals the derivative of u of f of t times the derivative of f of t. So that's just like our old chain rule we're used to, where we take the derivative of the outside times the derivative of the inside. We have the dot product rule. The derivative of u dot v is the derivative of u dot v plus u dot the derivative of v. And then we have the cross product rule, where u cross v equals the derivative of u cross v plus u cross the derivative of v. So let's go ahead and prove just a few of these. So let's start with proving the constant rule. So we have the derivative of vector c, where c is a, b, d, and these are constants. Well, if we take the derivative of this, we take the derivative of each of our parts, so we get 0, 0, 0, since the derivative of a constant is 0. Next, let's prove the cross product. So if we have the derivative of u cross v, we need that to equal u prime v plus u, or we need that to equal u prime cross v plus u cross v prime. So if u is u1, u2, u3, and v is v1, v2, v3. So if we take u cross v, we have I, j, k, u1, u2, u3, v1, v2, v3, going across, take the determinant. So we get u2, v3 minus v2, u3 times I, minus u1, v3 minus v1, u3, j, plus u1, v2 minus v1, u2, k. So we can write that as the vector u2, v3 minus v2, u3 comma, u1 v3 minus v1 u3, comma, u1 v2 minus v1 u2. So now we're ready to take the derivative of each part. So the derivative of this first part, well, we need to use a product and a difference rule. So we get u prime 2v3 plus u2 v3 prime minus the quantity v2 prime u3 plus v2 u3 prime. We get u1 prime v3 minus v1 u, or minus u1 prime v3 plus u1 v3 prime minus the quantity v1 prime u3 plus v1 u3 prime and then we have u1 prime v2 plus u1 v2 prime minus the quantity v1 prime u2 plus v1 u2 prime. So now the question is, does this equal u prime cross v and u cross v prime? Well, what do we get when we solve that out? So if we have u prime cross v plus u cross v prime, well, that will give us I, j, k, u1 prime, u2 prime, u3 prime, v1, v2, v3, which is giving us u2 prime v3 minus v2 u3 prime, comma, u1 prime v3 minus v1 u3 prime, comma, u1 prime v2 minus v1 u2 prime, plus we have the cross product of u and v prime. So plus the vector u2 v3 prime minus v2 prime u3, u1 v3 prime minus v1 prime u3, u1 v2 prime minus v1 prime u2. So when we add these two together, we get the vector u2 prime v3 minus v2 u3 prime plus u2 v3 prime minus v2 prime u3. And we can check that, and if we bring in this negative sign, we see that's equal. And then we can continue. So we got, for our second component, we get u1 prime v3 minus v1 u3 prime plus u1 v3 prime minus v1 prime u3. Again, we can compare, and we find that they're equal once we distribute the negative sign. And finally, we find that our last component, u1 prime v2 minus v1 u2 prime plus u1 v2 prime minus v1 prime u2. We find that that is equal to our third component up here once we distribute this negative sign. Alright, so there we have proved the cross product rule.